All right, hello and welcome to the last chapter of your Xi book, Probability. Are you ready? Let's do this. So, before we get started, psych, we're going to talk about the final and the last extra credit opportunity first. Okay, so week 18 is the week of the final. There's no classes, it's just final exams for everybody. And so I'm going to make this module available for you. And the first things that I will release are this final info page and the extra credit assignment page. So if you go to both of those, let's take a look and see what is going on. So the final is going to be on the Tuesday of finals week, okay? So not the Monday like I'm sure everybody else is planning, but the Tuesday. And you'll be able to complete it either on that Tuesday or the Wednesday after, okay? So it's the same kind of time frame that I've given you on the midterms, just starting on a Tuesday this time. May 18th is a Tuesday, okay? And the 19th is a Wednesday. So this is the range that you get to take the exam in, all right? Because it's a final, I'm going to give you a little bit of extra time. It's going to be a 2-hour exam. It's technically supposed to be an hour and 50 minutes, but I'll give you 10 extra minutes, because why not? And also, in this class, the final is worth the same as a midterm. So I'm really just going to make it the same length as a midterm, and you'll just have a ton of extra time if you need it, just to do as good as possible. Okay, so because of that, because it's also worth the same amount as a midterm, I'm not really going to make it cumulative unless the chapters that it's going to be on require information from previous chapters, which they probably do. But this is what I'm going to focus on. All right, here are the chapters that will be on the final. Everything after the second midterm stuff. That's all. Same for the homeworks. Everything after the second midterm required stuff. Okay, and so same with the lectures from week 11 on until the end, where this is the last set of slides that is part of the book. Okay, so yeah, that is the idea. It will be the same as midterm 2. You'll have some multiple choice and some short answer questions. I might ask you to like type up what you're thinking, but not like millions of paragraphs. At most, maybe a few sentences if I ask you to write stuff. But yeah, that is the idea. Open book and open notes as usual. Can't talk to another human unless it's me. You can come to my office hours, of course, while you're taking the final, and I encourage you to do so. Okay, so that's that. That's the first one. Then we have the extra credit assignment. Okay, so I want you to take a look at that as well. This one's the big one. So this will be up to 5% extra credit if you're willing to do it. So yeah, you have two options, just as usual. Make a review video. This time you can make it up to 40 minutes in length. Just go over stuff that will appear on the exam, as I've explained before. And then your option 2 is a write-up. Okay, so you can do that one if you would like. And again, the 5% option is you got to write 1,000 words, including code, if you include any code in your write-up. Okay, so that is the idea. Up to 5% extra credit if you're interested. Give it a shot. That is the extra credit opportunity, and I think that is all I wanted to say. Ask me if you have any questions about that stuff. And now let's get into probability. Are you ready? So here is some fun correlation is not causation examples, because we don't like those, right? Correlation has nothing to do with something actually having happened, okay? So that is what probability is all about, right? So let us do this. Per capita cheese consumption apparently correlates very well with the number of people who died by becoming tangled in their bed sheets over time as well. It's going up. People are eating more cheese and also getting more tangled and dying, apparently. So yeah, that is obviously not being caused by anything. It's not the cheese that's keeping people stuck in their beds. It's just a freak accident, okay, that these two things go along with each other, right? Same with this one. Apparently, the global warming, the global average temperature, it's increasing over time. Here are the years, and that is inversely correlated with the number of pirates, which is quite nice. Apparently, if the world gets hotter, there will be fewer and fewer pirates, or so this says. Okay, so none of this is true, and I guess the whole point of this chapter is to get you to understand that this is not anything that's worth caring about. Okay, so now it's time to actually learn about probability. So let's do it. And so for a nice pun, we're going to talk about this mathematical concept in probability theory called events. All right, so you want to discover what's going to happen, or try to estimate what's going to happen, right? When you're doing probability. So you make an experiment, we say. That's the technical term, right? And what an experiment is, it's just something that you do that gives you some outcomes, okay? So maybe like you flip a coin, you can either get the heads or the tails on this coin, and so you have two outcomes, right? You have heads or you have tails. And your experiment is flipping the coin, yeah? That is the idea. And so the set of all possible outcomes is called the sample space. So heads and tails is all you get, unless if you've seen the Twilight Zone episode where the coin lands on its side, which is probably never ever going to happen in real life. That is the sample space, right? The coin lands on either heads or tails. It's just a set. Everything's just a set. We know that now. And then an event, something that you're hoping for, something that you're hoping to happen, is just a subset of the sample space. So we're interested in how often we can land on just heads. So we will make our little event that is a subset of the sample space. Okay, that's what we're interested in, just the coin landing on heads only. We're going to see how long of a stretch we can get, maybe. All right, so that's hopefully not too bad, just new words in bold. And oops, I had a typo. So now we can get fancy and talk about probability distributions over a sample space. And what that means is we just have a function now. You can go from things that can happen, right? Your sample space, subsets of like possible outcomes, to a range between 0 and 1, right? So that's your probability. Like it's 0% ever going to happen, it's always going to happen, and you have probabilities in between 0 and 1, right? So this is just the interval from 0 to 1. And the idea is, it's supposed to, everybody's going to add to 1. So for every outcome in your sample space, for every little s and big S, the sum, this is really supposed to be right here, but it just sometimes when you typeset it, it goes to the side. The sum of all those little sample space, all those little events that could happen, should be 1, right? Because everything happening in total, you can't have extra, right? It should be 100%. That's the entire sample space. All right? So the probability distribution for a fair coin is going to be these two, right? You have two options. You have heads and you have tails, and the probability, which is some interval between 0 and 1, it should be stuck at 0.5 for both of them, right? So for heads, it's 0.5. For tails, it's 0.5. And they sum to 1, right? So the probability of heads plus the probability of getting a tails sums to 1, right? That is the whole idea of probability. All right. And then if you have an event that you're trying to figure out how often it happens, like maybe you have a 3-sided coin, or you're rolling a die or something like that, then maybe you want to figure out like how often does this die, if only I could draw a cube, how often does it land on either 1 or 2, right? And so then you have an event that's like, okay, I want to know how often it lands on 1 or 2. And so you just sum together all the little samples, all the little outcomes in that event. It's probability, right? So the probability of it landing on 1 and 2 is equal to the probability of it just landing on 1, plus the probability of it landing on 2. That's the idea. It's just summing it together. That is the idea of an event, a distribution, all these nice things. So that brings us to a special term. A uniform distribution is one that we like because we're not being cheated, right? So a uniform distribution is when you have a probability distribution where every outcome has the same probability. So a coins are uniformly distributed, right? Coin flipping. Coins have a uniform distribution. Because it's equally likely to have heads and tails. So are dies, like you can land on 1 just as often as you land on 2, 3, 4, 5, and 6, unless it's like a loaded die. They're all the same. That's the idea. That's the point. You're being tricked if like it's way more often going to land on a 2 than the rest, right? That's the whole point. This is not a uniform distribution. Something is more likely than something else. Okay, so we kind of like uniform distributions just as humans. It makes sense to us, but it doesn't have to be uniform when you have a probability distribution. Okay, so that is a lot of writing. Hopefully it's all making some sense, and let's continue. All right, so you can have events, just confirming that I'm still recording, that are mutually exclusive, like they don't both happen, okay? Two events are mutually exclusive if the two events are disjoint, okay? So this is the idea. Here is like one event, like your die lands on 1, 2, or 3, and here's your other event, the die lands on 4, 5, or 6. These are disjoint events because they don't share anybody. That's all. Okay? That's the whole point. And it makes it easy to find the union of these two events because you just sum them together. Okay? You just sum their probabilities together. If you want to get fancy, if you remember from last time the principle of inclusion and exclusion, it's all the same for combining events. Like the union of two events, if they have overlap, you have to subtract by that overlap. Okay? So like here's event 1, here's event 2. If they share things, like here are some outcomes, here are some shared outcomes. If you try to get the probability of both of these, you're going to add the probability of this and the probability of this, and you've overcounted these two in the middle twice, right? So you're going to use that principle again to subtract out anything that is in the intersection. Okay, that's the idea. You want the probability of a union of events. It's just the probability of the first plus the second minus the probability of that intersection. Okay, so it's just like counting. And this goes to 0 when they're disjoint. So it's just the sum, which is really nice. Okay. The complement of an event is also quite nice. It's just, well, it took, you use E bar for that. The probability of the complement of E is the probability of E bar, we say that. And it's just 1 minus the probability of E. Because, watch this, if like we're talking about dies again, 1, 2, 3, 4, 5, and 6, you want to know how often is it that you don't land on a 5 or a 6? Well, you just figure out, okay, what's the probability of this? Subtract it from 1, which is naturally going to be the probability of everything else. You see that? Because they sum to 1. That's the whole point. So you just subtract it from 1, and you have the probability of that thing not happening. Okay? So that's why we use the bar. It's like not in Boolean algebra all over again. Okay? A fun little example of using complements is to solve what's called the birthday paradox, if you've heard of this. It's a very interesting one because it makes no sense at all, and yet it's true. So the question is, what's the probability that you have a group of n people, and in that group you have at least 2 that have the same birthday? So how big of a group do you need to have a very high probability that people have the same birthday? If you just want it to be 50% possible that these 2 people, at least 2 people, have the same birthday in a group, all you need to get together is 23 people. Once you have 23 people sitting around, it is over 50% likely, just a little bit over, that there are 2 somewhere that have the same exact birthday. Isn't that crazy? That's very weird, but it's true. And the way that we solve this problem, how we discover that it's 50%, is that instead of this, we take advantage of the complement. It's a lot easier to find the probability that nobody in a group of n people share a birthday, okay? Because you have a bunch of disjoint events, okay? Also called independent here. We'll talk about that later. So here's the idea. How do you discover what's the probability that nobody in a group of n people have the same birthday? Let's do n equals 23 again. So nobody has the same birthday. What's the probability of that? Well, it's just, okay, the probability that the first person has a birthday, which is 365 over 365. It's, if you're a human, you have a birthday, so that is always going to happen. It's 1. And then event 2 is that next person that you're in this group that you're going to make has a birthday on a different day. It can't share it with this one. So this person can pick any day, but this person can only pick 364 days out of 365. Okay? We can multiply them to get the probability that all these 23 people have different birthdays. So that's that times. Then the third person has to have a different birthday than the first two, so they have 363 days to choose from, 365. And this goes all the way down to 365 minus 23 plus 1, I think, over 365. And so I will calculate this for you, and then I'll be right back, and we'll discover that it really is 50% when we take the complement. Okay? All right, so I've made a nice little racket program for us. I made a function called birthday paradox with a number n, so you give it how many people you want to figure out the probability of at least two having the same birthday. Okay, so we first get the probability that everybody in this group of n people was born on a different day. And so you start that probability at 1.0 and you start multiplying by 365 over that, 364 over that, on and on and on until we get to the end there. And so, yeah, from I starting at 365 down to this, because it doesn't get there, it gets to plus 1. That's what we wanted. Decrementing by -1. You just keep on multiplying this variable by itself, and that I over 365. Okay, so that's the probability of the complement, and then if we just not multiply, but subtract that from 1.0, we get the probability that there were people in this group of n that shared a birthday. Okay, what's the probability of that? It's the birthday paradox. So let's do it with 23. I promised we would do it. So the probability of the complement there, the probability that everybody in the group of n has a different birthday, is very, very close to 50%, right? It's surprisingly hard to do when you have such a small group even. So the probability that there are two people that share a birthday, at least, is 50. And so if you get a large group, like, I don't know, maybe you have a class with 50 people in it, the probability that you have two people that share a birthday is almost like 98%. It's in the 90s, right? 97%-ish. It's almost 100. If you have a huge class with 100 people in it, 99.999% there are people that share a birthday. Isn't that crazy? I guess this one makes a bit more sense than 23, but still, like 50? You have such a high chance still? That's crazy. So that's the birthday paradox. It's a fun one. Okay, so I've done a few problems. Now it's your turn. Let's do some by ourselves, and then we'll talk about how to do them together. So here is the setup. We have a drawer with some socks. We have white socks and black socks. They share the same amount, so n white socks and n black socks in this drawer. And so if I draw the drawer, we can go inside of it, like here's a little handle, and you can either have black socks, I'll just have those be black circles, or white socks, and you have the same amount of each, okay? And the idea is you are going to select two socks at random from this drawer. So you're going to pick out two, just closing your eyes or something, and it's equally likely, because you don't know the arrangement of these socks, like maybe you put the black ones on the left and the white ones on the right. We don't consider that. We just pretend we grab whatever we get, and it's random. So if that's true, if it's equally likely to select any two socks in any order, anyway, and the order that you select the socks in doesn't matter. So like, it doesn't matter that you picked this one first and that one second, as long as you pick both of those. Okay, that's the idea. So the order of those picking doesn't matter. Like, you pick that one first and that one second if you wanted. It's still the same group of socks that you picked. So with that all in mind, let's do A, B, and C. Okay, so first, how many ways are there to select those two socks? Okay, that is the idea. How many ways? And so maybe I'll probably need to make a new slide, but we'll see how well we can do with this. So give A a try, and we'll come back and do it together. So how many ways are there to select those two socks? And think about what you're doing. You're selecting two socks. You're trying to pick two socks in any order, Order doesn't matter. Remember where this is going. And how many socks do we have? 2n. Your brain should go immediately to this. 2n choose 2. That's exactly how many ways. We can make a subset of size 2 out of 2n things. See that? It's really not bad. All right, so A was stuff from last time. All right, how about B? How many ways of selecting the socks result in 2 socks of the same color being chosen? Okay, so think about this, and then we'll come back and do it together. So for this one, remember that you're picking from a smaller group now. Okay, so if you want 2 socks of the same color, you have to figure out how many different ways can we pick 2 socks that are black, and how many different ways can we pick 2 socks that are white. You see that? Those, you have to section them off like this, okay? Because you have to pick from this smaller group if you want them all to be black. You have to pick from this smaller group if you want them all to be white. See that? So that means, how many ways are there to select 2 black socks? Well, you have n of them, and you're trying to pick 2. That's it. That's how many ways you can select 2 black socks. And here's how many ways, same number, that you can pick 2 white socks. You see that? And so this is how the way that you could pick the black and the white. You just sum them together, and those are the ways of selecting 2 socks of the same color. Okay? So you have to do black separately and white separately, and they have the same amount this time. So it's really just 2 times n choose 2. Okay? You're picking from the black socks. How many ways are there to select just 2 of them? Okay? They have the same color in that case. All right? And that is the idea. We can sum these because they're disjoint, and because you can't have a black sock that is also white. That is the idea. So, did you get that one? It's a bit trickier to notice that you need to pick from a smaller group, I think. And then, finally, we need to figure out this last one. What's the probability that a randomly chosen pair of socks are the same color? We want to simplify this so that we don't have any chooses inside of this. Okay, so give this one a try, and then we'll come back and do it together. All right, so I think, if you think about it long enough, it's going to be the answer to B over the answer to A. Yeah? How many ways can we select 2 socks of the same color? If we just divide that by how many ways there are to select 2 socks, that's our probability, right? That is the idea. So we just need to divide this by this, and so let's get rid of these chooses everywhere. So 2n choose 2 is equal to 2n times 2n minus 1, right? Over 2 factorial, which is 2. Just 2 times 1, which is 2. That's that. We can simplify it that way, which is, I don't know if there's any easier way to do that right now. I guess we can knock off a 2, so it's like n times 2n minus 1 maybe. And then we have this one. So what's n choose 2? We'll do that over here. N choose 2, that's n times n minus 1 over 2 factorial, right? Which is just 2 times 1, which is 2 again. So that is this. And actually, we're going to multiply it by 2, so that's really nice. So that equals just n times n minus 1. That's good. That one's okay. Then we have this one. Okay, so it's just, this is how many ways we can do the thing we want, select 2 socks of the same color, and this is how many ways we can select just 2 socks. And so if we divide one by the other, we get the probability. Right, so it's going to be n times n minus 1 over n times 2n minus 1. And so it appears to be the probability is n minus 1 over 2n minus 1. Okay? And so that will be the final answer. Yeah, the idea is noticing that this is like this is the number of ways to do the thing, and this is the number of ways that the thing we could possibly have selected socks. Okay? That is the idea. So that is the answer. All right, let's do another one, and this one's going to be done a bit more systematically this time. So we're going to figure out the sample space and figure out the outcomes, and then we can divide one by the other, and that's how we get the answer, right? So our question is, which one is more likely? Rolling a total of 9 when you roll 2 dice, or rolling a total of 9 when you roll 3 dice? Okay, so which one is more likely to get a 9? And so let's figure out what we want here. There are 2 different experiments. It's like your 2 dice are thrown, or 3 dice are thrown. And so let's figure out the sample space first for each experiment. When you have 2 dice, the numbers that you get back, they look like this, right? The sample space for 2 dice. It looks like, okay, you could roll a 1 and a 1, or a 1 and a 2, on and on forever and ever. The space is, well, you can roll 1 through 6 the first time for the first die. And then for the second die, because these are like pairs of things, you can roll another 1 through 6. You see that? So this is the sample space for rolling 2 die, because you can roll any of these numbers for the first die and any of these numbers for the second die, and so you have a bunch of pairs of possibilities. And so for the same for S3. If you're going to roll 3 die, it's going to be, okay, 1 through 6 3 times. You see that? Because you're going to have options like, okay, you can roll a 1 and a 1 and a 1, or a 1, a 2, and a 2, etc. All the way on and on forever. All the way to 6s everywhere. Okay, so those are the sample spaces, and the outcomes that we want, or maybe the events that we want, are what we want to find. Okay, and we can just divide the size of each, and we will be happy. So let's figure out the event that we want for 2 dice, right? If we are rolling 2 die, we want it to total 9, right? So give this a try. Try and figure out how we should write this. Like, what are the events that we like here? Okay. What is the event we're looking for? How many different ways are there to roll a 9? Okay. So let's try and do this in lexicographic order if I can. It's going to be, this can't be a 2 here because there's no 7. So it's got to be a 3. And then we're forced to do a 6 there. Then we could roll a 4 and a 5. Then we can roll a 5 and a 4. Then we can roll a, let's see here. Then it's just 6 and 3, right? I think that's the event. That's all of it. That's every possible outcome that has a 9 when you roll 2 die. Yeah, 2 dice. I think. Now try E3. If you're rolling 3 die, what are the ways that you can get a 9? Okay, so give that a try. And then I'll do it here too. So can you have a 1 here? Almost certainly. You can probably also have a 1 here, because then no, 7. So this needs to be a 2. We're going to do it in order. And this has to be a 6. Okay? And then we have all these all over again. Oh no, what are all the different ways we could do this? 1 and then we have 3 and 5. Then 1 and 4 and 4. Then 1 and 5 and 3. Then 1 and 6 and 2. And I think that's all for that one. Now we have to do a 2 here. 2 and 1 and what is it? 3. And then we have a 6 here. So I'm not going to figure out how many of these are there. I'm going to write a program and I'll get back to you. So what we really care about is the size of these. Okay? What's the size of E2? That's just 4. Okay? What's the size of E3? I'll get back to you on that. I'll be right back. Okay, moment of truth. What did you get for the size of E3? All the ways, the event in which you could roll 3 die, and the sum of those 3 die is 9. So here's my program, and here are all the different ways, apparently. And the count is 25. That's what I found. So it's 25. And so the probability for rolling a 9 when you have 2 dice is size of E2 over the sample space when you have 2 die. And so we have that versus size of E3, so what's the event where you roll 3 die and you get a 9, over the size of S3. Okay? So what are these sizes? The size of S2 is 6 times 6. You see that? 6 squared. And then the size of S3 is 6 to the 3. That's all. So we need to discover which one's bigger, this number or this number. And it's still up in the air. So let's do, we have either 4 over 36, so 4 over 36, versus 25 over, what's 6 cubed? $216. Oh man, I'm not sure yet. We'll have to simplify these. All right, so 4, 36, that's 1/9, and then 25 over 216. That is not helpful. Exact to inexact. That's 11, 12-ish% versus 4 out of 36. Oh shoot, look at that. Look at how close that was. So it's apparently 3, okay? The 3 is better by just a hair. You see that? That's crazy. Okay, so apparently the answer is going to be 3 dice. You have slightly better odds of rolling a 9 when you have 3 dice, but not very much. Not very much better. Okay? So, yeah. Hopefully this is also what you got when you tried it. There's a lot going on here, but that's the point. That's why we're learning it. Alright, so another one for you. Let me get you started, though. So we're going to pick an integer randomly from this set. It's got 50 things in it, from 1 to 50. And so what's the probability that the integer that you pick is divisible by either 3 or 7? Okay? And my hint for you is, just like this last one, you split your problem up into different things, okay? Not different experiments this time, but different events. So let's have an event for divisible by 3, like the number that you pick is divisible by 3, and then another one for divisible by 7, and your job is to find this probability. Okay, so give that one a try, and we'll come back and do it together. All right, picking numbers at random. So what are all the numbers that are divisible by 3, right? E3 equals, well, you got 3, you got 6, you got 9, you got 12, all the way to, is it 48 is the last thing that's divisible by 3? We got that. And then, okay, what about E7? Well, you have 7, 14, 21, 28, 35, 42, I'm sorry, 35, yeah, isn't it 42? Yeah, 42, 49. And then we want to find this probability. So it's the probability of this union of events, and the issue is these, they're not disjoint, are they? For example, 21's in both of these. 21's in this one too, right? So we're going to double count. We have to use this rule. We have to use this union rule. So the probability needs to be subtracted by the probability of their intersection, okay? So the probability of E3 union E7 is equal to probability of E3 plus the probability of E7 minus the probability of their intersection. The event where they are both happening. Intersect E7. Okay, so let's find all of these, and that's the answer. Let's give myself some more room. So what is the probability of E3 happening? Okay, we have to figure out how many numbers are here, and then we just divide it by 50, right? So I'm a bit lazy, I might as well just write another program for that. So yeah, here is the program that I have made for you, and here's what I've done. So I've made, just keeping track of if numbers are divisible by 3, 7, and both, some helper functions, and we just loop through all of them and find out which ones are divisible by which. And so it seems that we have 16 divisible by 3, 7 divisible by 7, and 2 divisible by both, which makes sense because you got 21 and then also 42. Those should both be there. So that's 2, and I already lost count, 16, 7, and 2. 16, 7, and 2. And so the probability is you have 16 over 50, right? Because it's the size of the set. That's how many ways you can find something divisible by 3, plus 7 over 50 minus 2 over 50. So if we try and simplify this, what is it? 16 plus 5, so that's 21 over 50, so a little under half. Interesting. Okay. So it's quite common to find a number that's divisible by either 3 or 7, it seems. All right. So that's a nice little example. And so I forced you to do a bunch of things. This is good practice, I promise. All right? Okay, now it's time for a fun new topic called conditional probability. And the idea is that some very smart people noticed that if you know that some event happened, call it F, that tells you whether or not another one also happened. It gives you some good information. So there's the event F, here's like the event E. Let's do that. And of course there can be dots outside of this in the sample space that's not part of any of those events. The idea is, if I know that F happened, here's all the ways that F could have happened, that tells me something about whether E also happened, because here's their intersection. See that? It's like divide these dots by all these dots, and you have the probability of E happening after you know that F also happened. That is a good thing to know about, okay? So we like to call that the conditional probability, okay? The probability of E given F. And we write that with the pipe symbol, so the probability of E given F with that pipe. That's the probability of E happening after you know that F also happened, okay? And so the way to calculate that probability is to take the intersection and divide by the probability of F, okay? Because your new sample space essentially becomes F itself. Like that's all the different ways that F could have happened, right? And then you just divide all the ways that E happened inside of that. Because you know that F happened, you know you're sitting inside of this circle somewhere. How could E have happened too? So that's the intersection. And then you divide by the total number of dots, the number of ways that F could have happened. Okay? That's why you have this formula. And that leads to a really nice term, I guess. That's the right word to say. A really nice term called independence. Okay? So two events, they are independent. If you condition on one, it doesn't change the probability of it itself. Okay, so it's that is the idea. So if you know that F happened, and you try to notice, okay, how often does E happen when F happens, and that spits back out the probability of just E again, that means that those two events were independent. Conditioning on F told you nothing about E. That's the idea. You got no extra information. It was the same probability. Okay? So this is the definition of independence. Any of these bullets are exactly the same. Okay? So E and F are independent. When conditioning on F, trying to get E, gives you back E again. Same with the flip-flop. Conditioning on F, knowing that E happened, just gives you F again. Alternatively, you have this. The probability of E and F both happening. E intersect F is the probability of their multiplication, okay? This only holds when they're independent, okay? So all of these are the same. And here's an example of independent events. So let's try it with this first one maybe. So let's get the probability of E given F. So, and then also the E. So the probability of E in this example is 3 over 9, 3/9, which equals 1/3. The probability of F happening is 6/9, equals 2/3. And the probability of their intersection happening, intersect F, is 2/9, right? And, okay, what is E given F now? The probability of E given F equals the probability of their intersection, so 2/9. And then we divide by the probability of F divided by 2/3. Okay, that is equal to 2/9 times 3/2. The 2's cancel, equals 3/9 equals 1/3, and that's the same as the probability of E. What? So that told us nothing. It told us nothing about how often E happens. They are independent events, E and F. That's the idea. And when they're not independent, that gives you a really good clue, because like look at these two. This tells you that E is very, very likely to have happened when F happened. And a lot of the time in real life, these kinds of conditional probabilities work like that. Okay, you have non-independence, but when you do have independence, it's a nice thing as well. Okay, because then you can start multiplying things and solving that birthday paradox problem. It's all wonderful. Okay, so I think the last example that I want to give you before we go is called Monty Hall. It's a really, really fun, it's just, I guess it was a game show. I think it was a real life game show. I'm not sure if this exact thing happened, but something similar to it at least. Here is the idea. So you are on a game show, and the whole idea behind the game show is there are 3 doors, okay? Door 1, door 2, and door 3. And behind one of these doors is a car, okay? And you're not sure which. Like, let's pretend that the car is behind this door, and here's your fancy car. But you're not sure. And behind the other 2 doors are goats, and I'm not even going to try and draw a goat. But there are 2 goats as well. 1 car and 2 goats, and this is all shuffled. All right? And the way you play the game is you say, I would like to pick a door. Okay? So you pick any door you want, and you tell Monty Hall, who is the person who runs the game show, the announcer, and he's like, okay, you have picked door number 2. I am now going to open a door with a goat. Okay? And so he's going to open a door. And so maybe he opens this one, and he shows you that goat. And then he asks you, would you like to change your guess? Would you like to swap to the other door that's not yours and also not the one that I've opened, because you know that there's a goat there? Would you like to swap, or would you like to keep your original door that you picked? Okay? Would you like to swap, or would you like to stay? And the game is that, and the question is it better to swap or stay? Okay? That is the question. Okay? Is it better to swap/switch or stay? And it just so happens that it's always better to switch by a lot. And this, I think, is very unintuitive, right? And this is why I have this slide. It's a fun little example. So I'm going to try and prove to you hand-wavily that switching is better, and then I'm going to show you a simulation that I wrote in Racket that should prove it to you without any doubt at all. Okay? So, okay, here's the idea. Here's my hand-wavy proof to you. If you stay, probability of staying and getting the car, probability of staying and car, that equals 1/3, because the idea is you made that guess when all the doors were closed, and you had a 1/3 chance of getting the car. Okay, so that's 1/3, and the probability of switch, and you end up with a car, that happens to be 2/3, and I'm going to show you why. So, okay, here is what we know. We know that there is 1 car and 2 goats, and you picked this door. Okay, originally there was a 1/3 chance of you getting it right, which means there is a 2/3 chance that the goat is behind one of the other 2 doors. Do you see that? The goat is behind the other 2 doors with a 2/3 chance. And then Monty is going to open up one of those doors. Do you see that? So the chance that the goat was behind one of these 2 doors, or sorry, the car that was behind one of these 2 doors was 2/3, okay, behind one of these. And now we know that if the car is anywhere at all, still with a 2/3 chance, it's in this one. You see that? That's the idea. That's why it's 2/3. Car's in one of these with a 2/3 chance. Monty showed you this one, and so that 2/3 chance remains with only one door left. That's my hand wavy proof to you, okay? It's always better to switch. It's always better to try the other one because you're probably not right the first time, okay? That is the idea. And so I've written a simulation racket just to show you why it works. So here's my fancy program. I'm counting the wins that you get when you stay and the wins that you get when you change, when you switch. And I'm going to run 1,000,000 simulations. And here's my simulate function. I'm going to run this 1,000,000 times. And what I do is, okay, I randomly pick, okay, this door has the car in it, and this is the door that we've picked. It's all up to chance, right? And then we see if we won by staying, and then I figure out which doors we get to choose from, which one's going to be revealed to us randomly, and which doors we can change to, because it's quite possible that we picked the car the first time, and so we have 2 doors that Monty could pick and show to us. There's a lot going on here. And then we see if we won by switching, okay? And so I run 1,000,000 of those simulations, and I count how many times we won if we stayed and how many times we won if we changed, okay? So let me show you this, just to prove to you without having to take my word for it that it's always better to switch. Racket, let's enter Monty Hall.racket, and I'm going to run simulations. Whee! And so look at this. The probability that you win when you change, when you swap the doors, 2/3. Isn't that crazy? It's perfect because it is exact. We did the math. And you can rerun this. It's still random, but you, I think, can see that it's always better to swap doors. So if you're ever on this game show, now you know. And that is the Monty Hall example. And I think that is a good stopping point for us. That's like halfway through all of these. So I think we can come back next time and finish up these slides, and we'll start by remembering what's going on with our conditional probabilities. Okay, so I'll see you then.